Hi, everyone. In this lecture, we have just done the first lecture of gas law's experimental basis, and we'll come back to that, and I'll show you how to use those laws without knowing their names. But what we want to do first to get to there is look at the ideal gas law. So let's take a look at the ideal gas law. For the ideal gas law, the goals are to understand the origin of the ideal gas law and how to use the equation, to calculate the molar mass of a compound from the pressure of a known quantity of a gas in a given volume at a known temperature, and to relate gas density to molar mass, pressure, and temperature. So here's how we arrive at the ideal gas law. You might recall this graph here. This is the graph that we generated from data where we demonstrated how to get to Boyle's law. And here for the pressure and the temp, this is the graph we generated for Gay-Lussac's law. Now here for pressure in moles, this is I'm not sure whose law that is, to be honest with you, but this is the graph that we would generate for the relationship between pressure and moles. What I want to show you was how pressure varies with volume, how pressure varies with temp, and how pressure varies with moles. And so here are the three equations we get. The pressure is equal to kV over V. The pressure is equal to kT over T, or times T. And the pressure is equal to Kn times N. Now, what happens when we combine these three equations? Well, let's take a look. So here I've written the three equations again, only I haven't written them with a K in there. I've given the proportionality. Well, if this is pressure is proportional to 1 over volume and proportional to moles and proportional to the temp, we can combine these all together and get that the pressure is proportional to N times T divided by V. So here we can also turn this into an equation by using a proportionality constant. So in this case, the proportionality constant, I'm just going to call K, a general proportionality constant that involves N, T, and V. When we put everything in the numerator, we get PV is equal to K and T. Now in chemistry and most sciences that I know of, we don't use K as the abbreviation for the constant. We use the letter R. And we call that the gas constant. And so we get PV equals not RNT, but nRT. So this is written alphabetically. And this is the ideal gas law. Pressure times volume is equal to moles times the gas constant times the temperature in Kelvin. So here's the ideal gas law again. And you can see I can rewrite this by solving for R, and I get R is equal to PV over NT. Now, what are the units for pressure? It could be atmospheres. What are the units for volume? Liters. What are the units for N? Moles. And for T, it's K. So if we plug in a bunch of numbers here that are appropriate or related to one another here for the gas constant, we would come to the conclusion that R is equal to 0.0821 liters atmospheres per mole per K. So you say per before everything that goes in the denominator. Now, what if we were doing a problem where we were not given the pressure in atmospheres, but instead we're given the pressure in millimeters of mercury? What would we do? Well, it turns out that R is 62.4 liters millimeters of mercury per mole per K. These are two things that I would definitely write down on my little note card that I get for the exam. Here's some more information that we're going to need for this particular section. STP. STP stands for standard temperature and pressure. The standard temperature is defined as being 0 degrees Celsius exactly, which makes it 273.15 K with 5 sig figs, because the conversion between degrees Celsius and Kelvin is not exact. So if we remember these 5 figures, then we do have 5 significant figures for the temperature. The pressure is defined as 1 atmosphere exactly, so infinite number of sig figs, and 760 millimeters of mercury, also exactly. So you want to put that into your data bank too. STP is 1 atmosphere and 0 Celsius. For this section also, we use the density of a gas. So I want to imagine that I'm going to use the letter M for molar mass. You've seen me do that before. Usually I write MM for molar mass, but I'm just going to use one uppercase M here. The molar mass is determined by dividing mass by moles, so grams per moles, and that would be the molar mass. We're going to get this little m be the mass in grams and n be the moles. If I rearrange this, I get that the moles is equal to little m divided by uppercase m, or lowercase m divided by uppercase m. Remember, the lowercase m is mass, the uppercase m is molar mass. So here's my ideal gas law, PV equals nRT. So that means if I take N and substitute M over M, I get PV is equal to M RT over M. You, of course, have to know the differences between the M's. The one in the numerator is the mass, and the one in the denominator is the molar mass. Now I can take this equation and rearrange it, and I get that the pressure is equal to lowercase m times R times T divided by volume and also divided by the molar mass. Now the reason this is arranged this way is because M over V is density. So we can substitute D for M over V and we get that the pressure is the density times the ideal gas constant times the temperature divided by the mass. We can do a further rearrangement and we get density is the pressure times the mass divided by the gas constant and also divided by T. So these are important equations for us to remember. So this is an important one for the density, but we can also get the molar mass. If we take a look at this equation, we can write down that the molar mass of a gas is MRT over PV. Okay, so let's take a look and see how we use all of these equations. And we'll start with this one right here, the ideal gas law. So I'm looking for a piece of paper here, so I can show this one to you. So the nitrogen gas in an automobile airbag with a volume of 65 liters exerts a pressure of 829 millimeters of mercury at 25 degrees Celsius. What amount of N2 gas in moles is in the airbag? So let's take a look at some of the information we could write. So we could say the volume of the N2 is equal to 65 liters. We could say the pressure of the N2 is 829 millimeters of mercury. We could say the temperature of the N2 is 25 degrees Celsius plus 273.15. Okay, I'm going to get rid of that. And we end up getting 298.15 K. Now, this 25 is only good to the ones, so that means when we add these together, this is only good to the ones. But I'm not going to round yet. So I've got my volume, I've got my pressure, and I've got my temp. And then N, what amount? So the N of N2 is what we want. Now, is the nitrogen changing from one pressure to another? Is the nitrogen changing from one volume to another? Is the temperature changing? Is anything in this changing? And the answer is no. So there's no change in volume, There's no change in temp. There's no change in moles. And there's no change in pressure. Now, when you have a problem where nothing is changing, I call that a static problem. So static means nothing is changing. Okay, so if you have a static problem, you want to use the ideal gas law. So we want to use PV equals nRT. And since we want N, I'm going to rearrange this so that I get N on one side and everything else on the other. And by doing that, I can then plug numbers into this along with units, and everything should cancel very nicely, and I should end up with moles. So let me take this and write it over here. But when doing so, let me put in the proper numbers. So the pressure is 829 millimeters of mercury. The volume is 65 liters. The R, I'm going to leave that off for now. The T is 298.15 K. So the question is, which R do I want to use? Do I want to use R is equal to 0.0821 liters atmospheres per mole per K? Or do I want to use the one that is 62.4 liters millimeters of mercury per mole per K? Which of these two do I want to use? And the answer is, well, since that's millimeters of mercury, I want to use this R that has millimeters of mercury. So I'm going to write 62.4 liters millimeters of mercury per mole per K. And if we see what cancels here, the Kelvin cancels out, the millimeters of mercury cancels out, and let's see what else cancels out. The liters cancel out. And so if the liters cancel out, if the millimeters of mercury cancel out, and the K cancels out, I'm only left with mole. And this mole is going to work its way up into the numerator so that our answer will end up being moles. So as always, I like to do a little bit of estimating to find out what my answer is going to be before I plug it into the calculator. And so here, there's a number of ways we could do this. I think what I'm going to do is the easiest thing. 65 divided by 62 is 1. So 300 goes into 829, almost 3 times, but not quite. So we'll call it 2.5-ish for our final answer, around 2.5 moles. So let's see what we get here. 829 times 65 divided by 62.4 and divided by 298.15. And we get 2.9 moles of nitrogen. Now, why only 2 significant figures? And it's because of that 65. So that's the ideal gas law applied to basically a gas in a bag or a gas in a container, if you want to make it very general. Okay, so let's put that to the side. And let's take a look at this one here. Density and molar mass. Calculate the density of carbon dioxide at STP. So we need to recall what STP is. So do you recall what it is? The temperature is minus, 273.15 K, because it's 0 degrees Celsius, and the pressure is 1 atmosphere. Okay. And if you recall that equation, let's see, what was that? We had that the pressure is equal to the density times the molar mass times the temperature over V, if I remember right. Oh, no, That's wrong. Oh, geez, I'm just going to have to derive it. So PV is equal to nRT. So that means P is equal, or PV is equal to little m over big M RT. So P is equal to M over V RT over big M. So here, pressure is density RT over molar mass. Okay, so this means I need the molar mass of CO2. So CO2, we've got 12.01 for a carbon and 16 for an oxygen. So that ends up being 44.01 grams per mole. Okay, so now we can use this equation here. And since we're calculating the density, we're actually going to say the density is PM over RT. So now that I have density on one side, and that's what I want, I can just do a plug and chug. Of course, you want to show your units. So the pressure here is 1 atmosphere. The molar mass is 44.01 grams per mole. Now the R, we're going to use the one with atmospheres in it. So that's 0.0821 liters atmospheres per mole per K. And the temperature is 273.15. So here you can see that the Ks cancel. You can see that the moles cancel. You can see the atmospheres cancel. So the only thing you're going to be left with is grams and, let's see, and liters. Liters didn't cancel. So grams will be on top and liters will be on the bottom. Now, if we estimate this, this is a little harder to estimate, but here's how I generally do it. This 0.08, I round to 0.1 or 1/10. Now, I know it's not 1/10, but it's kind of close. So what's 1/10 of 273? Well, it's 27.3. Now, clearly, this is not 1/10, it's 0.08, a little less. So rather than say 27.3, I'm going to drop that down by 5 and say, well, I'm really talking about 22. So how many times will 22 go into 44? 2 times. So I expect my answer to be around 2 grams per liter. So let's see what we get here. 44.01 divided by 0.0821 and divided by 273.15. And we get 1.96. Let's see, we've got 3 significant figures here. We've got 4 here. We've got 5 here. And we've got an infinite here. So we're going to go with 3 significant figures for our answer. So 1.96 grams per liter. And that's your density. Okay. Let's take a look at one more problem here. Calculating the molar mass of a gas from pressure, volume, and temperature data. You are trying to determine by experiment the formula of a gaseous compound you made to replace chlorofluorocarbons in air conditioners. These deplete the ozone layer, which protects us. You have determined the empirical formula is CHF2, but to determine the molecular formula, you need to know the molar mass. Okay. You find that a 0.100 gram sample of the compound exerts a pressure of 70.5 millimeters of mercury in a 256 milliliter container at 22.3 degrees Celsius. What is the molar mass of the compound and what is its molecular formula? Okay, so first thing we want to do here is we want to get a formula that will allow us to calculate the molar mass. So we just did this problem a moment ago. And we have this equation here where the pressure is equal to the density times R times T over M. Or we could say MRTVM. Okay, I'm writing both of these down. And let's write down the information we have from all of this. So first we have the formula is CH4 or CF2. And if we get the molar mass of this, it's approximately 13 plus fluorines, I think, are 19. So you double that and you get 38, 39 plus 12 is 51. So that's 51 grams per mole. We have that we have a 0.1 gram sample. So little n is 0.100 grams. It exerts a pressure of 750 millimeters of mercury, or 700.5 millimeters of mercury. And we have that the volume is 256 milliliters, which I have the feeling we're going to have to convert to liters. So I'm going to do that right away. 1 liter over 1,000 milliliters, which is 0.256 liters. And we have the temperature is equal to 22.3 degrees Celsius, which we also want to convert right away. And we get 0.45. And then we get 295. So that's 295.45 K if I've added these up correctly. Okay, so this is all the list of the information that we're given. And we want to get the molar mass of the compound. So I'm thinking that since I have the pressure, since I have the mass, since I have the temp, and since I also have the volume, I want to use this form of the equation, P equals mRT over V. And I'm going to change this to, instead, molar mass is equal to, okay. And the idea here is that if we know the molar mass, we should be able to calculate the molecular formula. Because recall that if you take the molecular formula molar mass and divide it by the empirical formula molar mass, you get a multiplier. So we should be able to figure out what the molecular formula is since we know the empirical formula, and presumably once we have the molar mass, we'll be able to figure out the multiplier. Okay. So let's get to work here. So I'm going to rearrange this equation, and I'm going to get that the molar mass is little m RT over PV. Now, if I've done this correctly, when I'm done, I should get grams per mole. So let's find out. The mass is 100 grams. The R, since I've got millimeters of mercury here, I'm going to use the 62.4 liters millimeters of mercury per mole per K. For the T, we're going to use the 295.45 K. And then for the pressure, we're going to use 70.5 millimeters of mercury. And then for the volume, we're going to use 0.256 liters. So you can see that the liters cancel, the millimeters of mercury cancel, the K cancels, we'll be left with grams and moles, which is what we should have for our answer to get the molar mass. So estimating again, let's see, how can we do this? Well, we could say that 62 over 70 is pretty close to 1, but a little less. That would be fine. And then we could say 0.1 times 29.5 is, or 295 is 29.5. And so 29.5 divided by 25, or 0.25, should end up being a pretty big number, right? 295 divided by 0.25. This should go into that. If this were 1, it'd go into that. Oh, 29.5. If this were 1, it'd go into that 30 times. But if it's 0.25, it should go in like 120 times. Now, I'm not going to say 120. I'm going to say it's close to 100. And the reason I'm going to say it's close to 100 is because I know that this divided by this is not really 1. So instead of 120, I'm going to drop it quite a bit. So the answer should be about 100. And let's see what we get. 0.1 times 62.4 times 295.45 divided by 70.5 and divided by 0.256, and we get 102. Now, because of this, and because of this, and because of this, and because of this, we're only going to get 3 zig figs out of this. So 102 grams per mole. So now to get the real formula, we take the 102 and divide it by the 51, and 2 is the multiplier. So that means we take our formula CHF2 and we essentially multiply it by 2, and we get C2H2F4. And there is your chemical formula of the compound. All right. Thank you for listening.